Okay, so the work package 3 is about nonlinear periodic structures, and there are 4 of us working in this area. Myself, Paulo, who was speaking a moment ago, Vinicius Clianchi, who is a postdoc, and Jean Carneiro, who is a doctoral student. And all 4 of us will be talking today. And we're not necessarily going to talk about nonlinear periodic structures. We're going to talk about something slightly different. Put the next slide on, Paula, please. So what we're going to talk about is the concept of predicting the behavior of a finite periodic structure. And note that it's finite. And it consists of n elements, and these n elements are monocoupled. And what the theme of the presentation is about is how to predict the behavior of this structure. So when I say behavior, what I mean is that on the left-hand side, you see there's a vibration source. And what we want to determine is how that vibration propagates through the structure. And so it propagates to the right, and how much of the vibration gets to the receiving structure. And we're going to do this just by looking at a single cell. So you see in the diagram there, the small nth cell is pulled out. And what we look at is the transmissibility of that single cell. When I say transmissibility, what I mean is the displacement transmissibility, which is the displacement on the right-hand side. You are divided by the displacement on the left-hand side, UL. And what we do is we focus in on this quantity for a single cell. And once we've got that, we can predict the behavior for the whole structure. And we focus in quite specifically on the stop band behavior of the structure, and more specifically, the lowest stop band. So the stop band which has the lowest frequency. And we do this because this is probably of most interest from the point of vibration control. So the way we characterize the vibration of a single cell is to use the transfer matrix, which you see on the left. And the transfer matrix relates the force and the displacement on one side of the cell to the force and displacement on the other side of the cell. Now you can describe this, the dynamics of this cell in a different way if you wish. You can characterize it in terms of a dynamic stiffness matrix, or you can characterize it in terms of a receptance matrix. But the transfer matrix is actually really convenient to use in this case. Next slide, please, Paula. So what I'm going to do now is to further restrict the problem to one where we use symmetric elements. Now, when you have an infinite structure, it doesn't matter whether your elements are symmetric or not. But when you have a finite structure, then it does matter. And if you can formulate your problem such that you have symmetric rather than asymmetric elements, then further insight can be gained. So In this slide, we restrict ourselves to just looking at symmetric elements. And you see that the overall behavior of the system, so that is the transmissibility relating to the displacement on the right divided by the displacement on the left, is given by that large expression there, 2 divided by those two quantities in brackets. And you'll see that it's just a function of 2 things. It's a function of the transmissibility of a single element, which is the red letter T, and the number of elements, n. And the transmissibility of the single element is related to one of the elements in the matrix, the transfer matrix. It's related to T22, and it's the reciprocal of T22. And so if we know what the characteristics are of a single element, specifically the transmissibility, we can easily calculate the behavior of the whole structure. And so the reason for doing this is that, as you'll see, as the next presenters talk about their specific problems, you'll see that the analysis is significantly simplified because we're just looking at one element. And further to that, if you can just focus on a single element, then experimental work becomes much more easier as well, because you only need to look at a single element in the lab, and it's very easy to measure the transmissibility just using an impact hammer or a shaker and 2 accelerometers. Next slide, please, Hannah. So the question is how does this relate to the more traditional way of viewing periodic structures? And this was established quite a number of years ago by Dennis Mead. In fact, he wrote a very nice paper in 1975, where he established the relationship between a single cell and the whole structure. But just to remind you, if you take the transmissibility, the transfer matrix of a single cell, as you see on the upper left, then for free vibration to occur, okay, on an infinite periodic structure, then that transfer matrix has the form, as you can see, it's a diagonal matrix of the form where the diagonal terms are e to the mu. Now, for free waves to propagate, mu must be imaginary. If mu is real, then we get exponential decay. So if mu is imaginary, this actually means that cosh of mu is bounded between +1 and -1. And cosh mu is simply 1 over the transmissibility for a symmetric element. So if we look at the figure on the right, what we plotted here is the transmissibility of a single cell, and it's a very simple single cell. But you can see that there are 3 regions. There's 2 shaded regions which are in yellow, and you can see that in those regions, then the transmissibility is greater than 1. And if the transmissibility is greater than 1, then this means that cosh of mu is within the bounds of + and -1, and so we get free waves occurring. So the shaded regions are passbands, so free waves propagate in the structure. But in between these, you can see that the transmissibility drops below 0 dB, so it drops below unity, And what this means is that free waves no longer propagate. And so this corresponds to the stop band. And this is the focus of all of our studies. And there are three particular things which are of interest to us. One is the frequency that gives us the lowest frequency of the stop band, which is the red square. The other is the upper bounding frequency of the stop band, which is given by the black triangle. And the third quantity is the minimum or the maximum attenuation, which is the minimum transmissibility that you get within that stop band. And so what you will see over the next 30 minutes or so is how we use this framework, and we try to determine these three quantities, the two bounding frequencies and the maximum attenuation, for different problems. Next slide, please. So the three problems that we're going to look at are the use of symmetric or asymmetric elements. And Gian Cornero is going to talk about this. And Gian has done a study concerning this with rods. Then Vinicius will talk about the super stop band behavior. This is some very recent work that he's been doing. And then finally, Paulo will talk about some work that he's been doing where we use nonlinear springs to see what effect that nonlinearity can bring to some of these things that I've been talking about. So let me now hand over to Gian, who's going to talk about symmetric and asymmetric elements.
Okay, good morning. I am Gian, and let's talk a little bit about this, how Professor Mike has introduced these relations of transmissibility and infinity and symmetrical structures. And also, actually, when we look to infinity structure and we set, for example, some regions in this infinity structure like here, even that this set like A and B looks like a symmetrical or asymmetrical structure, this in terms of completely element will be symmetrical. So this behavior are equal. So that regions and that bounding points that Professor Mike talked a few minutes ago doesn't change for any one of this. However, when you are interested in practical cases, it's useful for us look for finite structures, right? So now there is a huge difference on this behavior, and we make this question, right? What are the effects of the cell symmetry can bring to that region that we are interested? That is the first stop band, right? So for example, so in the figure C, we have an symmetrical structure, like with a symmetrical cell, and D, an asymmetrical structure with some consistency in his properties, right? So it's a periodic rod. Please, Professor. So we can define in a generic monocoupled transmissibility, displacement transmissibility, as showing this stop equation here, stop expression. So again, is we can say is a simple expression that depends only on the number of cells and the elements of a single transmissibility, a single cell, right? So T11 and T22 are the diagonal elements of this cell, right? When we are looking for first, in this case, a symmetric structure, T11 and T22 are equal. So this expression can suffer a huge simplification. What is interesting in math terms, right, in mathematical manipulation, it's a good one, right? And also mu, as shown, depends only of this transmissibility, right? As we are talking about geometrical periodicity in rods, these transmissibilities are function of the frequency and area properties. So B and A and we'll define that alpha, small alpha that we have written there. So let's first consider this condition where B is greater than A and see what's happening. Professor, please move. So when we increase the number of cells, we see that the bounding points of our stop band, of our attenuation band region, right, is delimited by the same frequencies that is the stop band. So in symmetrical finite structures behaves like infinite structures. So we have this bounding points. If we flip this cell, so now let's make A greater than B, the behavior is the same for symmetrical structure. However, when we are looking now for asymmetrical ones, T11 and T22 are no longer equal, right? Because of asymmetry, these expressions, these terms are not equal, and it is not easy define clearly expression when the number of cells is large, but we can study clearly for one cell. So before we move the animation, let's see for let's the animation start again, please, and we see for one cell first. And when we have one cell, we can see clearly this region marked by these green lines that we call it attenuation band. This region is greater than the region of the stop band, right? Showing us there is the first difference between asymmetrical and symmetrical elements. And when we increase the number of asymmetrical cells, this banding tends to be the same as the stop band. So essentially what's happening is how you make your number of elements large, you reduce the effects in the boundaries, and this tends to behave in the same way as symmetrical elements, right? If we flip this structure now, you can see for one cell, now A is greater than B, and there is no longer a stop band, right? There is no longer an attenuation band. What we see is a huge resonance peak in the same frequency that before we have clearly a minimum transmissibility. And now what is happening is that our rod is behaving like we have a base excitation in the B section of the structure, right? Within that frequency has the highest dynamic stiffness, so promoting this quarter wave effect resonance peak there, right? So now we have seen what's happened with the bonding points, or what happened with our bandwidth. So for symmetric structure, this bandwidth remains constant to any number of cells. And for asymmetric, this bandwidth starts greater than the stop band and tends to be the same as the stop band. Right? But what happened to the minimum transmissibility? If you look for the dashed black lines right in the middle of the stop band where the minimum occurs, you see that has a difference in attenuation for asymmetrical and symmetrical structures. See? So let's see what's happened. Next slide, please, Professor. So imagine that we have a structure with 8 cells, and we measure the minimum transmissibility between each of these 8 cells. Right? So in the move, we will see that the divergence between symmetrical and asymmetrical minimum transmissibility happens just in the last 2 cells, right? So the blue line here is for asymmetrical one, and the black is for symmetrical one. So the rest of the points in my structure has almost the same minimum transmissibility, but in the last 2 bits, the last 2 cells, we have this divergence, and this divergence range a maximum of 6 dB. So where comes this 6 dB from, right? So let's look for that frequency, 1/4 of wavelength, the minimum transmissibility there. So for an asymmetrical attenuation, asymmetrical structure, the minimum can be written in terms of area rated over raised to the powers of n, right? Which is simple in practical terms. And symmetrical structures can be defined like this expression also. So if we made an alpha raised to n large, this will tend to be 1/2 or 6 dB. So this is where it comes from, okay? We can also provide some experimental works to see this behavior. So here we have 3 asymmetrical periodic cells in a nylon rod. So we first excited from the left-hand side, so UL, and we look for the transmissibility excite in this direction. So we can see clearly this attenuation band region, right? So, however, when we excited in the opposite direction, so now we're excited in the right-hand side, not in the left, we see that amplification happen where we have the attenuation band. So, I know it's a lot of information in a quick space of time, but the aim here is see there is a huge difference on the behaviors of asymmetrical and symmetrical elements, and is useful. We use asymmetrical elements, but has this point: they must be correctly orientated. If we intend to have an attenuation band, we must orientate them in correct way, right? Using the point with the lower receptance point, that is the thinner part of the rod first, right, as excitation connected to our vibration source. Right? Otherwise, we will have an amplification. So these are the aim points when we are looking for this. And also, the transmissibility approach, as we saw here, can provide us a nice expressions to predict all these bounding points. We are not going through all this analysis here, but it's possible to get this, and we get these expressions. Okay. Now I will pass to Vinicius to talk about the super solvent.
Okay, good morning, everyone. Can you hear me? I am Vinicius. I am the postdoc student from the work package 3, and I will talk a bit about this super stop band. Paulo, can you go to the following slide? Okay, an alternative way to obtain an improved stop band in a periodic structure is by introducing a resonator type device. The advantage of these mechanisms is that it introduces 2 attenuation effects. One is the local resonance, and the other is the Bragg effect. And the combination of these 2 effects create what we call the super stop band. So it was shown that we can predict the behavior of a periodic structure with any cells by predicting the behavior of a single cell. So in this study in particular, we investigated a single monocoupled symmetric periodic cell with a vibration absorber attached. So in the left figure is presented a photography of the experimental setup and the schematic of the cell, where the bolts and nuts and the washers are the end and the central masses, and the PVC rings are the springs of our structure. At the central mass, it was attached a beam-like tunable vibration absorber. This absorber is shown in the right figure. We can observe it in this absorber that the masses were made adjustable, so we can easily change the absorber frequency without the need to change the device or the absorber mass. So we can easily change the tuning frequency of our device. Please, Paulo, go ahead. So let's first considering that our structure has damping. So here it's presented an expression for the displacement transmissibility. We can easily see that it is controlled by 2 fundamental parameters: the mass ratio, mu, and the tuning frequency, gamma, which is the ratio between the absorber and the host cell natural frequency. The mass ratio, it's important because it controls the attenuation level. However, it is the tuning parameter which controls where the stop bands will occur and which type of stop band they are. So let's considering the figure on the left. It is presented a comparison between the measured in the experiment and the predicted from the analytical analysis. If the tuning frequency is smaller than 1, 2 stop bands can be observed. One due to the local resonance introduced by the absorber anti-resonance, and the other due to the stiffness-like Bragg effect, introduced because the absorber is being excited at a frequency greater than its natural frequency, and then the absorber has a stiffness-like behavior. Go ahead, Paulo. When the tuning frequency is greater than 1, again, we can see that the 2 stop bands occurs. However, they occur at different frequencies. So at the first, in the lower frequency, occurs the mass-like Bragg effect, and later at higher frequency occurs the local resonance stop band. When the tuning frequency is exactly equal to 1, the local resonance stop band combines with the Bragg stop band, creating the super stop band, where the super stop band, it has a wide bandwidth with high attenuation at the minimum, at the central frequency. Go ahead, Paulo, please. So we can understand why and how to obtain this super stop band by analyzing the top view of the displacement transmissibility in function of the frequency and the tuning frequency. The hot colors in this graph correspond to the resonance frequency, and the cold color line correspond to the anti-resonance introduced by the vibration absorber. The black dashed line here corresponds to the stop band bounding frequency. If we select a slice of this graph, for example, for gamma equal to 0.8, we can easily note that the first stop band occurs due to the anti-resonance. We can easily see that the anti-resonance is passing through this range of frequency. And the second will be due to the Bragg effect. The same occurs if we select another slice, but now for gamma equal to 1.2. However, this anti-resonance now occurs at higher frequency. However, to obtain the super stop band, we need to tune the vibration absorber so the anti-resonance coincides with the resonance frequency here in the middle when gamma is equal to 1. Moreover, this super stop band only occurs because at this tuning condition, the 2 internal bounding frequencies, capital omega 3 and capital omega 4, occurs at the same frequency, and this also coincides with the anti-resonance frequency. So at the same time, the vibration absorber adds the mass and stiffness-like Bragg effect to the periodic cell, the anti-resonance acts directly on these 2 internal bounding frequencies, so that they are no longer a bounding frequency, and we can have this wide bandwidth with this super stop band in the case. Go back, Paulo, please. But as we can observe it in the left figure of the super stop band, in the experimental result, a valley may occur inside this stop band. This can be explained by the damping in the structure. So go ahead, Paul. So at the optimal tuning condition, the absorber is tuned to the host cell resonance frequency. And at the resonance frequency, the system dynamic is controlled by the damping. So, of course, the damping will play an important role in our structure. So, in the case the host cell damping is greater than 1, which is shown in the right figure, okay, a valley may occur at the same tuning frequency. If the host cell and the absorber has the same damping, we can see that we have a smooth super stop band. However, when the host cell damping is smaller than 1, a peak may occur inside the super stop band, and this is shown in the left figure. Okay, so why this is occur? This is occur because the most part of the vibration introduced in the periodic cell is being transmitted by the left hand mass of the periodic cell, is not being transmitted to the absorber mass. So this is the reason why we have this peak inside the super stop band. So to obtain an effective super stop band, we need to correctly tune the vibration absorber so we can break the two internal bounding frequencies, and we need less damping in the absorber than in the host cell. So then we can have a good super stop band. So now I give the words to Paulo.
Thank you, Vinicius. So now this is a talk about the initial investigation on the use of nonlinearity to improve the behavior of periodic structures. So what I'm going to talk about first is we need to answer this question: if we have any advantage of using nonlinearity to improve this behavior. So before that, we realized that we need to answer two questions first. So the first question is, we need to understand what's the limitation in the performance for the linear system. And then on the top of that, we are going to investigate how we can use nonlinearity. The second question is, what source of nonlinearity we are considering? So I'm going to start with question 2, just to clarify for those who have not worked with nonlinearity before. We are looking only nonlinear stiffness, which could be of these three types here. It could be a hardening type of stiffness, and we can use a polynomial to represent the restoring force. So in this case, we have a linear part here. So this is a linear coefficient, and U is the displacement. And there is another term here that controls the nonlinearity. So this S3 is the nonlinear cubic stiffness. So when both of these coefficients are positive, we have this sort of hardening effect. So as we stretch the spring, it gets harder to deformate. So that's why you call hardening. So the linear case is, of course, the case that most of you probably know. So it's just a linear coefficient. But we can also have this other configuration here, which we call softening, which occurs when you have this coefficient which is negative. There is another configuration of this spring that you can have, which we call bistable, where you can get when you have a negative linear coefficient. Sorry, this should be S3, but and a positive cubic coefficient. But for now, we are not looking at this condition because it brings other sorts of responses. What is important here, and I think this is really important, is that for low displacement, you can see in this box that all the springs behave similarly. So it doesn't matter if you have a nonlinearity. If your displacements are small, you are not going to have any effect of nonlinearity. So I put this because we are only going to observe this phenomena when we have large displacement, probably near a resonance frequency. Okay, so now the first question is, what are the limitations in the performance for a linear system? So again, we are looking at a finite monocoupled periodic systems of n cells. And in this case, we are studying two configurations. We didn't enter in the resonance case where you have a vibration absorber yet, but we are looking at these two configurations. The first one is we have two rods, and we have put a nonlinear spring right in the middle of these two rods. So you have a parallel configuration of the rod and this set of nonlinear spring and viscous damping. And the other configuration is this one, that we put the set of nonlinear spring in series configuration with two rod sections. I'm not going to talk about this on the right today because we don't have enough time for that. But one thing for sure that we can say before looking any result of this is that if we want to reduce the transmissibility, which is the displacement on the right over the displacement on the left for this condition, it's very straightforward to see that if we make this stiffness very, very strong, very hard, you are going to block this displacement in the middle, and so you have zero transmissibility. So a good configuration for this would be having a hardening spring. And in this other configuration, to avoid transmissibility, the best case is that we don't have any connection between the two cells. So this is something very straightforward for me. I don't know if it is for you, but we don't have to look for this now. But a good configuration would be having a softening spring in the middle. So first, let's discuss this case, and maybe in the future we can go to the second case in another meeting. So first, as I said, we need to understand the linear case. Again, we are looking at the transmissibility as one of our main target quantities. So the transmissibility for this system is actually given by this equation. So this is the spring stiffness. I didn't put the damping here, but I plotted with some damping. And E is the Young modulus for the rod, A is the cross-section of the rod, and K is the wave number. So this is how the transmissibility looks. And as Mike said just in the beginning, we can plot a dispersion diagram if the structure was going to be considered infinite. And we see that this is related to the transmissibility by this expression. So when we see a trough, or these troughs here on the transmissibility, they correspond to the regions, this shaded area, where you have attenuation in the dispersion diagram. And you change the phase in the dispersion diagram every time you cross one of these resonance peaks on the transmissibility. So why I showed this is because we are not going to be able at this moment to calculate the effect of nonlinearity on this graph here, on the dispersion diagram that you are probably used to. But everything that changes here, we need to think about that is going to affect also the dispersion diagram if our structure was going to be considered infinite. So some features of these transmissibility functions are these. We have this minimal dashed line that follows the troughs. So this follows this expression here, which we can obtain by combining these trigonometric functions. So this is important, and we are going to see later that the nonlinearity doesn't affect this trough. And the reason is that because I said it's going to affect the regions where you have large displacements. So other features of this transmissibility is that some bounding frequencies are controlled by fixed roots. So every time this 2KL equals to pi, so this term here becomes 0. So you have cos of pi, which is -1, and you get these values here where the transmissibility in dB is 0, but it's actually 1, right, in absolute values. So these red marks, they don't change. It doesn't matter whatever you put on that rod, can be linear or nonlinear. These points here are not affected. Also, you can see that some of these red marks, they correspond to resonance when you look the receptance, and some of them, they correspond to some other values which are not resonance. So this second resonance is not going to change. If we have nonlinear stiffness, we are going to see that, and this other one is not going to change. Secondly, there are other routes where the transmissibility equals to 1, which I plotted with these green circles here. And to find them, you need to solve this equation. So actually, they are stiffness dependent. And also, some of these are related to resonance. This first one is related. The second one is not. The third one is related. So if we make this stiffness nonlinear, we are probably going to see some effects on this first resonance and on the third because it has large displacement. So let's see that. So to obtain a function, we are using harmonic balance, so we can represent in frequency domain the spring force by this expression here. So our transmissibility changes a bit. So we get this extra term right here. And we can see that the problem of finding the dispersion relation is because we depend on some internal degree of freedom. So to find the transmissibility, we need to solve this using some nonlinear root finding algorithm. So the effects are these now. So it doesn't have any influence on the minimum because at the minimum U1 is going to be very small. So it doesn't change anything. It's not going to have any influence on these red marks because these frequencies are fixed. And it might have some influence on this first and third peak that I'm going to show you by the last slide. So this is the last figure that I'm going to show you. The red curve here is the linear case for the transmissibility, and the blue one is the nonlinear response transmissibility. So what we get here, as we can see, is a shift in the resonance. The first peak moves towards higher frequencies as an effect of the hardening stiffness. This frequency doesn't change, and this frequency doesn't change, and this one also moves towards higher frequencies. So the effect is this: we get an extra bandwidth using the nonlinearity just for one cell. Of course, there are other secondary effects that I'm not going to discuss today. You can have jumps and things like that in the frequency domain, but there is no time to discuss. Maybe we can discuss this on questions. And this is a zoom for the second peak. So we get this extra bandwidth here as a result of the nonlinearity. It's not much, but it's something that we can get. So I'll end up showing some of the publications for this group, which is going to be, I'm not going to say everything, but there are some papers that were already published and some that are coming. One has been submitted and a second round of review, and 2 are being prepared. So I end up saying thank you and to everybody and to FAPESP for supporting this. Thank you very much. So I was going to ask Carlos if he could help managing the questions, if anybody would like to make questions.
Yes, of course. So we are open for questions and comments.
Yeah, another thing, Carlos, if people think more comfortable asking questions in Portuguese, it's okay.
Okay, of course.
Maybe we can switch. We decided to present in English to record, but if you want to make questions in Portuguese, is that fine, Mike?
Sure, no problem.
Yeah, there are some questions here on
From the chat.
Yeah, Jean, could you answer that, please?
Yes, but first, Professor Mike, you has your hand up. You want to do some comment? I see your raise your hand where Paulo was talking about nonlinearity.
No, that was a mistake.
Okay. Bom, então qual que é a diferença do attenuation band e do stop band? Essa foi uma questão de nomenclatura que nós adotamos para definir essas duas áreas. O stop band, você pode encontrar ele, você pode visualizar claramente, por exemplo, usando a curva de dispersão, né? Mas o attenuation band você não vai ver numa curva de dispersão, porque ele é para estrutura finita, né? Então, e tem um outro detalhe do attenuation band, que é essa característica dele ser maior do que o stop band, né? Então, por exemplo, você tem o que a gente chama de upper attenuation band, quando a estrutura assimétrica é igual a 1. E aí, esse attenuation band ele vai reduzindo até o stop band conforme a estrutura vai aumentando. Então, foi uma forma da gente diferenciar essas duas regiões onde as ondas não se propagam, né? As duas regiões de atenuação, tá? Não sei se foi claro, se consegui responder. Eu falei um pouco rápido, né, pessoal, mas essa é a ideia. Mas...
We have another question from Rodrigo Nicoletti. How do you create nonlinear spring in practice? I think this is for you, Paulo.
Okay. So, Rodrigo, one easy way of having that is using magnets. So this is a point that we are performing on the lab recently, but you can configure hardening effect having two repelling configurations of magnets, and you can have a softening spring having a attracting magnet. You can also get this if you have some geometrical configuration of some stiffness element, like if you have a spring assembled horizontally to the displacement. So these are some things that we are investigating to put in practice this. I don't know if I answered your question.
Obrigado, Paulo.
Vinicius, another question for you. How did you define the natural frequencies to determine the gamma ratio? Are they uncoupled natural frequencies?
Paulo, can you go back to the previous slide, please? Yeah. So how we can define the natural frequency to correctly tune the vibration absorber? We have to tune to the natural frequency of the right end mass. Okay. So when the central mass is fixed. So this is how we need to correctly define the natural frequency. So we need to tune the vibration absorber to correspond to this natural frequency. So then we can make the vibration absorber behave similar to the right hand mass. Okay. And about the second, go ahead, Carlos, sorry.
Yeah, you can go ahead. The other question is, how robust is the super stop band to small deviations of the gamma parameter?
Yeah, this is a problem that we are trying to see how can we can manage to solve this, because it is not too much robust. Because if we change a little bit the tuning frequency, we can see that a peak appears inside the super stop band, and it's a peak different from this one that we have here. This value here occurs because of the damping on the structure. But if the absorber is not correctly tuning, we have a small difference, and then a peak can occur. So we are trying to investigate some ways where we can make this tuning frequency more robust and avoid that a peak can occur inside the super stop band.
Can you, I could just add a comment. Paulo, can you put the previous slide on, please? Yeah, right. Okay, so it's really important that you have the ability to tune the vibration absorber when it is fitted to the structure, okay? Because it is very sensitive, as Vinicius said, and if you were to fit this vibration absorber and you didn't make it tunable, i.e. you could not move these masses, then the chances of you achieving a super stop band would, without this problem in the middle, would be very difficult. So Vinicius, I believe, had to be very, very careful in tuning this when it was in situ.
Yeah.
Thank you, Mike. Thank you, Vinicius. Another questions, Vinicius, you again. How do you know that you have a super stop band? Do you have the band structure?
Just I'm trying to understand the question.
Just a comment. So
yeah.
Everyone is welcome to open the microphone and make questions or comments or discuss some answers. Please go ahead, Vinicius.
Well, we do believe that some kind of damping device could improve this attenuation effect, but the main feature of this super stop band of connecting this resonator device in the structure is to break the bounding frequency. So when we can correctly tune this the absorber to the structure, we can break the behavior of the two internal bounding frequencies. So they are no longer a bounding frequency, and we can have this very nice super stop band. a damping device could improve the attenuation, of course. And it's the same case, we can easily see the effect of the damping on the absorber. So when the absorber has less damping than the structure, we can even improve the performance of the super stop band. But as we have seen, the easiest way to have an improvement in this stop band is by connecting this resonator device, so we can break this bounding frequency.
Mm-hmm. But have you calculated the band structure and really checked that you have two band gaps? A resonant and a
well, we have defined that by observing the behavior of the anti-resonance effect. Okay, so when we change the damping on the Paulo, can you go to the last slide, please? Okay. So in the super stop band, we can obtain when we exactly tune it to the host cell resonance frequency. And we can understand how the local resonance effect is acting on this bounding frequency when we observe the effect of the damping on the structure. When the host cell damping has much less damping than the absorber, we practically remove the local resonance effect on this periodic cell. So we break the super stop band in two stop bands. So we didn't have find the expression to calculate this how much this absorber anti-resonance has of effect on this tuning frequency, but we can easily understand that is the anti-resonance on the occurring at the same frequency of the bounding frequency that is bringing this coupling effect of the local resonance with the Bragg effect.
Okay, thank you, Vinicius. The other one is from Matheus Basílio. Paulo, how do you plan to obtain dispersion diagrams for the nonlinear structures?
Okay, so yeah, this is a trick question, which even for me it's hard to understand and difficult to explain. But let me try to get it to our minds. So dispersion diagram, it's really nice, but it's when we are looking at infinite structure. Okay, so free wave propagation, infinite or semi-infinite. So in this case, we are probably not going to see resonance, because resonance occurs when you have reflection, so you have peaks. Nonlinearity occurs when you have this large displacement forced at a harmonic excitation at a frequency that has large displacement. So we can discuss free wave propagation going through nonlinear elements, but in my opinion, this can be compromised by the fact that we are not going to have very large resonance behavior. That's something that I'm trying to put on my mind, and maybe this is a good point to discuss here. So other part is, if you have finite structure, then we are going to see some resonance. And then we can look the effects of the nonlinearity. So what I'm trying to do it here is trying to relate the transmissibility back to the dispersion diagram in a different way. Instead of looking at the dispersion diagram and try to predict what's going on in terms of quantities like displacement, or I'm trying to do a opposite direction study. So if I change my transmissibility here, I'm also going to look some changes in the dispersion diagram if the structure was going to be infinite. I don't know if it was clear for you, but what I would expect if you look the last graph here is that if we could associate this transmissibility to the dispersion diagram, we are probably going to see some improvement in the bandwidth where you have attenuation in the dispersion diagram. I don't know if it was confusing. It is confusing for me, but it's a good point to discuss, I think.
Paulo, damping was considered in this simulation?
Yeah. We need to put some dump. Maybe I can. For the dispersion diagram, no. For the dispersion diagram, no.
No, for the nonlinear results.
Yeah, we need to put some damping, because if you don't have damping here, so you have some unbounded frequency response due to the resonance of this mass over this spring here, which is one of the resonances in the system.
Mm-hmm. Thank you, Paulo. Yeah. So Brennan thanks Vinicius and Mike, and he asks, maybe some kind of broadband damping could increase the robustness of the super stop band. I think Vinicius has.
I think I have answered this already.
Yes. So next one from Edson Jansen. The symmetric and asymmetric examples in the beginning of the presentation can also be proposed considering different materials instead of different section areas. Issues related to locally resonant band gaps can also be studied in the symmetric and asymmetric examples.
The answer to the first part is yes. We chose to simply look at different areas, but you could choose different material properties. So yes, indeed. And are there issues related to locally resonant gaps if you've got symmetric or asymmetric system? The answer is yes again, but this is current work. Vinicius was in fact, I think he's studying this at the moment as we speak. So I think it's probably too premature to talk about that. But yes, there are some issues associated with symmetric and asymmetric systems using an absorber to get a super stop band.
Thanks, Mike. Oh, please, have you finished?
Yes, sure.
Okay, thank you. So I think we can combine the next two questions from Huda and Thiago. They are asking if it's possible to extend the results shown from the monocoupled system to multi-coupled systems.
Again, we're currently looking at this. The one thing that stands out with the monocoupled system is that if you look at the transmissibility of a symmetric cell, then the bounding frequencies are the same as the stop band, and they don't change no matter how many cells that you attach. But that's not true if you have, let's say, beams connected. But it can be almost true. Okay, so what you can do is you can learn quite a lot, or at least we believe that you can learn quite a lot from studying the transmissibility of a single cell, but you cannot take those conclusions and relate them directly to a structure with many cells. But you can gain some insight into what will happen.
Just to add to this, Mike, we have looked for the cases of beams on pinhead supports. So we get a monocoupled configuration if we have periodic beams on pinhead supports, but dispersive wave propagation. So some features, we can observe some features related to the case of monocoupled periodic systems with non-dispersive wave propagation.
Thank you. Paulo, another question for you. Did you test the convergence of the harmonic balance for higher order harmonics?
Yes. This is, of course, this is an issue because when we are trying to calculate this using some very simple analytical expressions, we need to approximate the nonlinearity force. So one thing that we did, but I didn't have time to show, we did some numerical integration. So the difference is that we have, using harmonic balance and analytical solution, we have a exact solution of the continuous part of the structure in an approximation of the nonlinear force. And then we have done this using finite element method, where we have an approximation for the continuous part of the structure and exact force response. And it does follow some features of the last figures I showed you. So of course, if we start increasing the force and displacements, other harmonics are going to be present. We need to take care of that. But in case of rods, the displacements tend to be very small. So it was not the case for the problems we were looking until now. Good question, yeah, thank you.
Thanks, Paul. More questions or comments? No questions?
Yeah. So, Carlos, may I add some comments in the end? One of the reasons we have done this presentation was to show some of the things we've been doing. Of course, we didn't show all the detail, but we would like to have chance, if anybody else would like to contact us, this group of people working with this kind of devices, this experimental data that we showed. We are very happy to share and discuss if you want to talk with us.
Good, thanks, Paul.
Yeah.
So I think we had a good number of questions and discussion. So if you don't have any additional questions, we can end up here this meeting. So thanks everyone for attending. We will have another meeting in the same format on May 3rd.
Mm-hmm.
So I think it's Professor Arruda's group that will present. Is it? If I'm not mistaken.
Yes, I think we had agreed on us being the second work group to present.
Great. If the DPIs can stay on this room, we can discuss some things related to the project. Thanks.
Okay,
Thanks.
Carlos, if you, there's a question that occurs to me.
Mm-hmm.
May I proceed?
Of course.
Before moving to the next phase, okay. So thanks for the colleagues who presented. Very nice work. The question that comes to me is that maybe for Paulo and Mike, by considering nonlinear effects, what would expect is to have benefits such as increasing the band gap mainly. So do you have a positive conclusion about that? It seems to be that it's not clear yet what benefits we can obtain from, let's say, exploring nonlinear behavior. What's your feelings about this?
Can I add to this question, Domingos?
Sure.
Because adding to what you've just commented, Paulo, if the nonlinear effects will show up in resonance situation, and when you build a band gap, is to avoid resonance. So it may be a paradox there. If you want to use nonlinearity to avoid resonance, is it possible at all?
Yeah, that is what we are trying to answer in this package. Yeah, so far there are other configurations like using non-linear vibration absorbers, like oscillating elements that we have not discussed it and we have not looked in detail so far. So for the rod case, it's very marginal, the gain that we get, because to start with, longitudinal vibration is very small, so you need a very strong nonlinear effect to see some difference in these very tiny displacements on rods. So, but what we get is only increase in the bandwidth where you have some attenuation. That's what we have seen so far. Next thing that we are going to look is trying to translate this to beam vibration. So we have other displacement, but for the rod, we didn't see a very good. Even the other configuration I show you in series, rod in series with nonlinear spring is not very. I'm not sharing, but that one that have a rod, a nonlinear spring, another rod. It's also not very good because you get some good attenuation, but you have those problems with softening springs, which causes some instability in the system. Would you like to add something, Mike, on your view so far?
Yeah, I think that I think the observation is an interesting and somewhat obvious one in hindsight, right? That we need to have resonant behavior in order to make use of nonlinearity. So I think an obvious place to look is in terms of the vibration absorber, and it's possible even that you don't use the nonlinearity in a dynamic sense, but you can use the nonlinearity in order to create a relatively compact vibration absorber which has a lowish natural frequency. So we can tailor the stiffness of the absorber so that it behaves almost like a linear absorber, if you like, but at a lower natural frequency. And in a sense, that's what we've been doing for quite some time with vibration isolators, trying to achieve that. And I think we might be able to achieve something similar, but for sure it needs to be focused on the absorber, in my view.
Yeah, thank you. I think you have given a very good answer, because you're right that in the case of local resonance band gaps, as the name says, you have local resonance. So the resonators will resonate. So they will have large amplitudes. By the way, I think this is something that I haven't seen much treated in the literature. When you design a metamaterial with resonators, what is the amplitude of the resonator vibration? It might be unrealistically high, depending on how you design it. And that's where probably you can use very easily nonlinearity caused by high amplitudes.
Yeah, yeah. Yeah, but just to finish, by these configurations I show you, maybe it's not a good way to investigate. We discovered that after some time suffering on this, but it needs to be done.
Yeah, but you could perhaps do something with bistable elements. I know there's a guy in Purdue University working on bistable elements there, and maybe using those in to obtain these non-reciprocal type waveguides, perhaps.
Yes.
Perhaps there's a use there.
Yeah.
Yeah, but in my opinion, you have a nice, work, ongoing work. I think I appreciate this. Let's say more fundamental studies where you develop equations and you look the effects. Yeah, very nice. This enables us to have a good insight on not only the mathematics, but also on the physics of the problem. Very good. Congratulations.
Thanks, Domingos. We are all limited by our abilities, and so we are limited in terms of the complexity of things we can study.
So, more comments or questions? So thanks, Mike. Thanks, Paulo, Jean, and Vinicius for this great presentation. It was really, really good. Congrats.
Thank you.
Thank you very much, guys. See you in the following meeting.
Thank you.